Thank you very much. I'd like to start by thanking Debraj, Sivaguru, I'm not sure he's here, Sivaguru and Diganta for inviting me to this workshop, and it's been very, very valuable. Thank you so much. And to give an opportunity to give this two-part talk. Okay, so the title had the words peak function in it. So probably that's a good place to start. Let's begin with the definition. What is a peak function? Well, it depends on what you want it to mean. I'll talk about what my context is. So let omega be a proper subdomain of Cn. And let's pick a boundary point in omega. So a function f that is, so this is a function that's going to live on the closure of omega. So a function that is holomorphic on omega and is continuous on the closure of omega is a peak function if, well, in some sense it peaks, so the definition will clarify what that sense is. If, let me call this phi, because I have too many functions in this talk, so let's start with a Greek letter. So if, say, phi at this boundary point is 1, and the absolute value of phi of z is strictly smaller than 1 everywhere else. That is, mod of f of z is strictly less than 1 for all z in omega closure minus p. So now I'm strictly not going to need this definition, but let me just put it on the board so that I can spend a few minutes talking about the utility of this stuff. So this time I'm looking at a function phi, which again is going to be holomorphic in this proper subdomain. And I want its domain of, it's okay for its domain of definition to be slightly smaller than in the first example. I just want phi to be defined on omega union this boundary point p, and phi, if phi is continuous there, then I call this is a weak peak function. So the weakness here signifies somewhat smaller domain, slightly lesser regularity, if, well, all of the above continues to hold, which is to say phi of p, phi peaks at the point p, and phi, the absolute value of phi is strictly smaller than 1 everywhere else. So you have this time for all z simply in omega, right? So why do I care? Why do I care for these definitions? So please note that the definitions don't say anything about whether, if I give you an arbitrary proper subdomain and a boundary point, whether the domain will at all admit such a function, right? So that's when that happens is part of the theme of this talk. So let me maybe say a few words about the utility of this. No, a priori not. But there should be a non-empty topological boundary, and hence this is why I'm calling it taking omega to be a proper subdomain. So utility, well, there's actually a lot I could talk about in this area, but I'll just give 2 instances. Okay. So again, I'm just going to throw some words at the audience, and people who are interested can look up the literature on this subject. But in Professor Stauber's lecture, we saw results which came from the realm of the abstract theory of uniform algebras. And that is one of the utilities over here, that if now, as Diganta you mentioned, if omega is relatively compact, then in fact, this class of functions that are continuous on omega and holomorphic in the interior, this forms a Banach algebra where the norm is with respect to the subnorm. Right, so such algebras are called uniform algebras. So under this hypothesis, you have a uniform algebra and the existence of, or well, not the existence, but the description of the set in the topological boundary of admitting, well, I'm not going to be very pedantic writing this down, the set of all points in the boundary that admitting peak functions. So the closure of such a set happens to be a species of boundary. We saw today a species of boundary called the Choquet boundary. So this is important from the uniform algebra's viewpoint. Right? So this is all I'm saying. Yes, if I do have time, sometime in my second lecture, I might actually pick up any one of these instances and flesh them out a little more, okay? But that is time permitting. So here's another example, and this is about, so you've seen these invariant distances that have been defined, right? Strictly speaking, these are pseudo distances, but with omega, once again, bounded, recall the distances. So you saw the Kara-Teodori distance and the Kobayashi distance, right? So once omega is bounded, then by definition, both of these are true distances. And so you have a metric space. And one would like to understand the geometry of these metric spaces. So in general, it isn't even clear whether these distances are proper. Another way of putting it, it isn't clear that these metric spaces equipped with the relevant distances are Cauchy complete, right? So above notions, by above I mean those notions, these are important in diagnosing when these metric spaces are Cauchy complete, when either of these metric spaces is complete. Right? So time permitting, one would like to revisit them. Okay, so these are two reasons that I am familiar with, comfortable with, as to why we care, right? So what I'm going to present today is not a genuine theorem, really. It is a meta-theorem. It is a theorem which tells you what are the conditions you need to have in hand. And these are not necessarily very simply stated conditions. So you would need other theorems to guarantee the conditions at hand under which one can say that a given boundary point admits a peak function, Okay, so that's the foreshadowing. But before I state the meta theorem, I suppose, of today's talk, let me put another term up here which I will need to state my theorem. And this is the notion of when a domain has a Stein neighborhood basis. So probably if you just pause that phrase, most of you here would figure out what I mean. But then since this is an expository talk and you have younger members in the audience, let me put this up. So let me just stick to relatively compact. Let omega be relatively compact in Cn. A family with, or let's say, a family omega sub alpha, alpha runs through some indexing set. This is a family of pseudoconvex okay, I just need omega to be open, but let's say this is a domain, just for sanity. So this is a family of pseudoconvex domains with every omega alpha being an open neighborhood of omega closure. So this gives me the Steinness part, this gives me the neighborhood part, and then the basis part is such that given any domain, let's say D, such that D that contains omega closure, there exists an omega sub alpha that is contained in D. Okay? So for some of you, this might... Okay, so I didn't say what I'm defining, right? So I said I have this family and I have these properties, so let me teach myself how to complete this sentence. A family, this, of pseudoconvex domains with this property is called a Stein neighborhood basis. Okay? This is called a Stein neighborhood basis. So, depending on how you think this through or whether you overthink this, it might seem like, okay, hey, you've made a definition, why do I need it? Don't at least domains that we are interested in this game, namely pseudoconvex domains, always have a Stein neighborhood basis? Well, if you're thinking in terms of strongly Levi pseudoconvex domains, then yes. But this is actually restrictive. Okay, so I want to just say this for the moment. I want to move on, state the main result, and then make a few more comments. Okay, so with this, I want to state the thing that I intend to prove over the next, I guess, 1.5 lectures. So this is a meta theorem. And I'm saying this just out of honesty because once I finish stating this, it'll seem like a very odd theorem because it'll seem to you that there are hypotheses that require theorems of their own. And that is exactly what is intended, okay? I don't necessarily know whether this, as stated, is written up anywhere. But then this is widely known among people who are interested in the question of when does a boundary point admit a peak function. And I want to say that this is a collage. What I'm going to present is a collage of techniques from techniques by. So I guess, to my knowledge, the place where the essential tricks are mentioned are in this paper by Pflug. Do I know which year this is? Probably I don't. I just said mid 1970s. And by Forness and Sibony, approximately 10 years later. Okay, so here goes. So let omega, okay, so now there are lots of hypotheses here. So let omega be a bounded pseudoconvex domain. Suppose. So now let me put down a few conditions. Under these conditions, one is guaranteed a peak function. So I should probably pick a boundary point, right? So let P be a boundary point. By the way, is this large enough to be visible at the back of the room? Yeah? Okay. So suppose. Okay, so I'm going to, instead of saying 1, 2, 3, I'm going to use letters to remind ourselves of what kind of conditions I'm putting. So this is a condition about the boundary geometry. Okay? So let me write this out carefully. There exists a neighborhood U of the boundary point P, such that omega intersect U is connected, and there exists an open connected subset. This is the outer limit, right? Further ahead. Oh, super. This is the one, right? All right. So there is a neighborhood of P, and inside of this neighborhood, there exists an open connected subset W of U, such that omega closure intersect U. So this is the portion of the closure of omega that sits inside this neighborhood. I remove from this the point P. And what I in fact get is a proper subset of this W. So there are going to be pictures, by the way. Okay, so do Oh, thank you. Oh, thanks so much. So you have this. So there exists this open connected subset W such that when I look at the boundary of W, and I just look at the piece of the boundary that's again sitting inside U, is a smooth submanifold, smooth hypersurface. let's just say submanifold, so that we know that this is not a patch, it's not a manifold with boundary. Smooth submanifold. So you have smooth submanifold of U that is strongly. Oh yeah, I should also say this. It might probably be deducible from everything I have written already. This is a smooth submanifold of U containing P and such that this hypersurface is strongly Levy pseudoconvex. So of course, you have this thing that's dividing the neighborhood U into two pieces. So I should tell you strongly Levy pseudoconvex viewed from which direction, right? So viewed from inside of W. Right. So this is strongly Levy pseudoconvex off the point P. Okay. So no bets on how this thing is at P. But when I draw a picture of what this is supposed to say, things will become a little bit clearer, okay? So this is the first condition. This is a condition on the nature of the boundary. The second condition I'm going to call LP. So this sort of is an explanation for the title of this talk, From Local to Global Peak Functions, okay? So the other element that I desire is that at the point P, there is a local peak function. I actually want something a tiny little bit more than that, which is that there exists a phi that is holomorphic on W, and its domain of definition is W closure intersect U, and phi is continuous there. Okay, such that phi of P is equal to 1, and mod of phi of Z is strictly smaller than 1 everywhere else. That is, for all Z in, how is this? This is W closure intersect U minus P. Okay, so LP here stands for the condition of existence of a kind of local peak. And the third condition, I'm keeping this room for drawings, okay? So, no, let me use this part of the board. My third condition, what is my third condition? Do I even have a third condition, or is this good enough? No. So this is, G stands for the geometry. So this is where I'm going to use this condition. So the third condition I have is simply omega. Omega has a Stein neighborhood basis. Okay? So with these conditions in place, then omega admits a peak function at the point P. Okay? So it probably, the fact that one has gone through all this song and dance suggests that in general, in higher dimensions, it is really difficult, unless I give you some special example with very special properties, really difficult to determine whether a given point on the topological boundary is or is not, is not a point that admits a holomorphic peak function. Okay, so I had told myself that I should make a comment at this place. Yeah. So let us talk a little bit about these conditions. Okay, how reasonable are they? So first, let's look at this. So these kind of go hand in hand. So these conditions so the condition B and the condition LP to actually ensure that one has these conditions is a part of any known proof, any known construction of holomorphic peak functions, except for very simple cases. Okay, so the comment I had told myself I should put up on the board is that these, so every known general construction. So by general, I mean, I don't, it's not a construction that involves a very special example about which I know everything, okay? So if I take some general family of domains, then every known general construction, or I should say prescription, for constructing peak functions involves peak functions, well, I should say, when omega is non-convex, right? So the theme of this workshop has been D-bar, so we have really not gone into, let's say, the affine geometry of domains. So maybe this is an exercise for the reader. Try to describe those convex domains where, try to describe those points on the topological boundary of a convex domain, geometrically convex, that admit holomorphic peak functions. Okay, so that's an exercise. So outside of the geometrically convex realm, every general prescription for constructing peak functions involves showing these two conditions, B and what have we? B and LP. I think this is literally a precise statement, but just so that what I say convinces you, there is a large subset of the audience here that gathered for this discussion meeting in January of 2018. And I believe it's either a group of 2 or a group of 3 people who presented this very, very delicate proof by Bedford and Furness about the construction of a global peak function on a very specific model domain. Right? Does this ring a bell among people who were at the discussion meeting? So now that model domain, in fact, osculates a given domain that is of smoothly bounded pseudoconvex of finite type. So these are osculating model domains, and for a small part of the for a small neighborhood around the point B, the boundary of this osculating model has all of these properties, whereby the Bedford-Furness proof gives you this condition for this patch. Okay, but every other proof involves some species of this. All right, so that's all I'm going to say. I want to come to this thing, which is interesting, because, again, it is an excuse for me to first address the question, are there any pseudoconvex domains with this property, right? Are there any pseudoconvex domains having a Stein neighborhood basis? Yeah, I'm going to, okay. Let me complete this point. Yeah, let me complete this point. So a few points. So a couple of observations. So any strongly Levy pseudoconvex domain admits a, say, probably add this for caution, admits a Stein neighborhood basis. And the reason for this is very simple, because the positivity of all of the eigenvalues of the Levy form determines an open condition. So you can wiggle outwards the boundary of such a domain, and you are in luck. So I do want to say, however, that this is limiting. And I'm going to just draw a simple example. So these here are strange axes. So this here is the axis that parametrizes mod of W, and this here is an axis that parametrizes mod of Z. Okay? And so given this, so this here is 0. So try to imagine in your mind's eye what's going on. This domain does not have a Stein neighborhood basis. Okay, so this condition is genuinely limiting. And in view of the crash course in several complex variables that Debraj gave you, at least the following shouldn't come as a shock to everyone, or to anyone, that the one phenomenon that's novel in several complex variables is that you have examples of domains where every single holomorphic function on that domain extends to a strictly larger set, right? So this is a version of the Hartogs theorem that you've seen. So what happens in this situation, this is again, it's sort of Hartogs whose name is frequently associated with this phenomenon. So let's say if I have a Stein neighborhood basis, in other words, this picture should tell you that there is an open set around the origin. So as soon as I have a Stein neighborhood basis, there is an open set of the origin that is contained inside a potential omega alpha. And a Hartogs phenomenon tells me that then every holomorphic function, in fact, extends to a bidisk. So this is what happens. And I think this has been mentioned to you that in Euclidean space, pseudoconvexity and being a domain of holomorphy are equivalent properties. And this extension to the bidisk tells us that any potential omega sub alpha is not a domain of holomorphy and is hence not Stein, right? So this is genuinely limiting. I do want to point out, and you'll sort of see this as one progresses with the proof, that there are alternative hypotheses I could place on. I can probably replace B and G with other alternative hypotheses. So when I get to the point that is a big deal in the proof, I will speak in greater detail about this. But then you've seen, for instance, a sufficient condition for guaranteeing the existence of local subelliptic estimates, right? This is the ability, so the property we are talking about in the terminology that's been introduced is the property P sub 1, all right? So I could, if anyone glancing at this, anyone sort of thinking deeply about the proof will realize there are other flavors of this theorem. The point I want to make is that I want sufficiently many of the assumptions in this meta-theorem to be those that are geometrically manifest. These are conditions that do not involve, say, an analytical overarching hypothesis, such as the compactness of the Neumann operator N1. Again, we'll see why that could help. What amounts to the same thing, the existence of a local subelliptic estimate. Instead, what I have is, boom, I have a condition that's geometrically manifest. The other thing is, I actually want to use the Hörmander L2 D-bar theory to give a proof of this. So since this is a workshop on L2 methods, the results by Kohn are very, very deep technical results, and they involve aspects of the L2 D-bar L2 theory, but other stuff. Here we sort of can pull this off by staying within the ambit of the L2 theory. So I've said, look, here are conditions that are geometrically manifest, so I should probably give you a picture, right? So let's look at a picture. Let's say this here is your omega. And let's pick a point. Let's say this here is the point P. So what this picture is telling us is that, let's see, let's use many colors. So it talks about a neighborhood of the point P with a certain property, right? So let's say this here is my neighborhood U. Okay, so there exists a neighborhood U that intersects omega nicely. Omega intersect U is connected. And then inside of there is an open connected subset W. And I require the portion of the topological boundary of W that sits inside U to be of a certain kind. So So this here is the portion of the topological boundary of W that sits inside U. So W is this part that I'm shading in yellow. Yeah? Now, in some sense, you might find this drawing objectionable. The experts might find this drawing objectionable because you might be thinking, you might be seeing a cup over here. And a cup on the boundary is going to be an obstacle to this condition, okay? This is just a schematic. So there is enough of bending in the other directions to ensure that this is strongly Levi pseudoconvex when viewed from this side, okay? So this is what condition B is telling us. And I actually want to start with the proof. So my 0th step of the proof would be a bunch of preparations. So let me now exploit the same drawing and put in a few more doodles. And these are going to be illustrations of the existence of a Stein neighborhood basis. So you have some stuff. You have some stuff. That's a technical term, right? Stuff. So you have these wiggles, which are just my schematic of the boundaries of lots of slightly larger sets. That happen to be Stein and which contain, so let's see, omega closure, yeah. So let me darken, thank you. I was actually thinking of doing this. Since I use the color white, I've kind of painted myself into a corner using white paint. This heavy part is the topological boundary. Right? So let me label. So this is the part. So I think I said this, but I should have written this down. So the thing that's shaded in yellow is my W, right? So you see, this is slightly larger than this, right? So this portion is omega closure intersect U. The portion shaded in horizontal hatching is W, right? So that's what's going on. So, yeah.
Why is P necessarily a boundary?
It is, but this is a smooth submanifold of U containing P.
Oh, there. Yeah.
Right. Okay, so now let me also clear some space for me. No, W is a superset, right? This is, you understand. So I'm not saying this. I think that was the confusion, right? Or rather, this is the icon. This is the icon I want to use. Right? Did I read your mind correctly? Ah, great. All right. By the way, before we get into deeper waters, any other questions? No? Okay, let's proceed then. So, given the time that I have, I will probably have the time only to make a key geometric preparation and state a d-bar result, okay? But let's do that. So proof. So it's sort of always annoying to keep writing z minus p. So my first step of the proof is, without loss of generality, let p be equal to 0. Right? This is absolutely without loss of generality. Now, so here's what happens. I'm not going to write this out. I'm just going to put a memo over here. So this is step 0 of the proof. Step 0. And this is the preparation step. Okay. So let's just pick a particular pseudoconvex open set that properly contains omega closure. Pick your favorite one. So among the various characterizations of such sets is that, so I pick an omega sub alpha. Omega sub alpha admits a smooth, strictly plurisubharmonic exhaustion function. Okay? So I look at the level sets of this exhaustion function, and I appeal to Sard's theorem. So there will be somewhere, say I pick this pink guy as my omega sub alpha. So there will be a smooth level set. There will be a smooth level set. And so there will be a smooth level set, and when I look at the smallest eigenvalue of the Levy form of this level set, it might be very, very small, but it'll be strictly positive. And this is good enough, and this is something I'm not getting into. It is good enough for me to wiggle this orange portion and this yellow portion. So this is where I use the fact that this yellow portion is strongly Levy pseudoconvex away from the point P, to do a bit of surgery so that I have, so this is the part where I'm waving my hands a bit. So, but I'm being pretty rigorous, though not writing it out. So first of all, well, how the hell are you going to get a hypersurface? Well, Sard's theorem is going to ensure that for you. And as I said, the smallest eigenvalue of the Levy form for that hypersurface, even if it's very, very small, it is positive enough for me to have some wiggle room. And so what I'll have is surgery will give me a slightly enlarged domain like so. And my omega, where is omega in all of this? This here is my original omega, right? So this doodle here is the boundary of omega, okay? And this orange thing is the boundary of a pseudoconvex domain. So this plurisubharmonic surgery gives me on the smooth portions strong Levy pseudoconvexity, so that what I have is, in fact, this orange stuff over here, which I'm calling omega star, is is what? Is a pseudoconvex domain, right? So let's write this down. Let's just make a memo of what I just did here. So the following tools what are the tools? Well, Sard's theorem. Well, first of all, a characterization of pseudoconvex domains that was the statement, unproven statement about exhaustion functions, Sard's theorem. And what else? And plurisubharmonic surgery. Give us this is important, the pseudoconvex domain omega star. And so this is the stuff in orange, Give us the pseudoconvex domain such that, so please note, this is what happens. I look at omega star and I remove the point P. So Pranav, watch carefully. Yes. So that's all history, right? Yeah. So you have, whoops, I should say this. This is what I want to say. This contains omega closure minus the boundary point P. All right? Okay, so in the last minute and a half, let me just indicate what I want to do. So step 2, this is constructing an auxiliary function. Auxiliary function. I'm not going to do the construction today, but I'm going to put up certain objects and put them on the picture over there so that tomorrow I will have the same drawing up on the blackboard, okay? So remember, there is this U. So this here is U, remember? So I pick a couple of relatively compact open sets around P. So this I'm going to call V1, and something a little larger that I'm going to call V2. All right. So, okay, so I'll probably take a minute or two. Oh, I see. Oh, right, this is the 55-minute mark. Great, thanks. So, constructing an auxiliary function. So, yeah, so you see, by hypothesis, we have this peak function, right? So the name of the game is to, well, not extend the peak function, that's kind of ambitious, but modify the holomorphic peak function where it exists so that it admits a holomorphic extension to the rest of omega, and the bounds that I want are obtained. Please note these are L infinity bounds. So this is somewhat alien to the the L2 theory at the first glance, okay? So all of this massaging is to be able to use L2 theory that has been rigorously proved in this workshop to be able to give pointwise bounds, okay? So since I said that I want to do a modification followed by extension game, we do the standard thing, which is we extend by 0 smoothly, right? So I need a bunch of cutoff functions. So I don't need this by hypothesis. So let 0, remember my point P is now 0. Let 0 sit inside, so both of these are connected open sets. So these are connected open sets. So V1 is such that V1 closure is a subset of V2, and V2 is such that V2 closure sits inside this U. All right. So now let chi1 and chi2 be two compactly supported cutoff functions, please note, on the bigger domain, omega star. So these are cutoffs. And they are like so. Chi1, restricted to the smaller of the V's, is identically 1. And chi2, outside of V2, is identically 0. And chi2 has the property that restricted to the larger of the V's is identically 1, and chi2 outside of U is identically 0. Actually, no. I am going to, so I actually am in the realm of the Hörmander theory. And so yeah, I'm being a bit, actually I'll just say this. So these are just standard global cutoffs, yes. Yeah, thank you. So what I had in mind was just standard plain vanilla cutoff functions. Thanks. And maybe I will end with this result. So Debraj has already talked about a result of this ilk. I will probably fill in a detail or two. So we will need, so this proposition. So let omega be a bounded pseudoconvex domain. And let 0 lie in omega closure. Let phi be of class C2 on, let's not say omega, I don't want to confuse this with what I have. So let's say D. So phi is of class C2 and plurisubharmonic, right? So given a form G that is, so I'm given a P Q plus 1 form, let's keep it simple, let's say 0. A form on D with the weight e to the minus phi, such that del d bar of G is 0, and this is in the sense of distributions, then there exists a form U with measurable coefficients satisfying the d bar equation, d bar of U equals G, and this estimate. The estimate is I have the integral over d, norm of U squared, e to the minus phi over, this may not immediately look familiar. This integral is less than or equal to the integral over d of the form, the square of the pointwise norm of g times e to the minus phi dv. Oh, there's something. Given this, there's a crucial thing I forgot. There exists a constant c, which depends only on the diameter of d, such that, so I should continue from here, such that given any data that satisfies the compatibility condition, I have a solution that satisfies this. So I'll stop right here, and I'll give a quick sketch of why we should believe this in tomorrow's lecture, and then carry on with the proof. Right. Oh yes, thank you. I did add the C, but didn't put it. Yes, thanks. All right, I'll stop here.